When we evaluate the surface integral, where the surface S is the part of the cone z squared equals x squared plus y squared that lies between the planes z equals 2 and z equals 3, let's begin by looking at the surface of integration, the surface S in space. The surface S is the part of the cone between these two planes where the lower plane is z equals 2 and the upper plane is z equals 3. If we look down on the xy plane or project the surface S onto the xy plane, the region R in the xy plane would be the region between this outer circle and this inner circle, so the region R would be this region here. For a surface S given by z equals g of x comma y that is continuous and differentiable over a region R in the xy plane, so the region R is the projection of S onto the xy plane, and g of x comma y and its partial derivatives are continuous over the region R, and f of x comma y comma z is continuous over the surface S, then the double integral over the surface S of f of x comma y comma z integrated with respect to S equals the double integral over the region R, where remember the region R is in the xy plane of f of x comma y comma g of x comma y times the square root of the quantity 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared differential a. So notice how, to evaluate the surface integral over the region R, we need to write the function f of x comma y comma z as a function of x and y by replacing z with g of x comma y, and then differential s equals the square root of the quantity 1 plus the sum of the squares of these partial derivatives, differential a. So going back to our example, notice how the surface S is not solved for z, but we can take the principal square root of both sides of the equation, because notice how we're only concerned about the surface of the cone when z is positive, or more specifically when z is between 2 and 3. So z is going to be equal to g of x comma y, which is equal to the principal square root of the quantity x squared plus y squared. So now looking at our formula here below, for our next step we'll find the partial derivatives of g with respect to x and y. Of course, if we want to, we can rewrite this as the quantity x squared plus y squared raised to the 1/2. So the partial derivative of g with respect to x is equal to the derivative of x squared plus y squared raised to the 1/2 with respect to x, which would be 1/2 times the quantity x squared plus y squared to the 1/2 minus 1, which gives us negative 1/2. And now applying the chain rule, we multiply by the derivative of x squared plus y squared with respect to x, which would be 2x. Notice how the 2 simplify out, so we can write this as x over, let's write this back as the square root of the quantity x squared plus y squared. And now for the partial derivative of g with respect to y, this is equal to the derivative of the quantity x squared plus y squared raised to the 1/2 with respect to y, which would be 1/2 times the quantity x squared plus y squared to the negative 1/2 times the derivative of x squared plus y squared with respect to y, which is 2y. So the partial with respect to y would be y divided by the square root of the quantity x squared plus y squared. Which means the given surface integral is equal to the double integral over the region R of, for f of x comma y comma g of x comma y, we'll substitute the square root of the quantity x squared plus y squared for z, and we'll leave these first two terms the same. So we have x squared plus y squared minus the square root of the quantity x squared plus y squared. So all this times the square root of 1 plus the partial derivative of g with respect to x squared, which would be this fraction squared. So we have x all over the square root of x squared plus y squared squared, plus the partial derivative of g with respect to y squared, which would be this fraction squared. So we have y all over the square root of the quantity x squared plus y squared, and this is squared, and then we have differential a. Let's continue evaluating this on the next slide. Let's simplify this square root here. All of this underneath the square root would be 1 plus, when we square this fraction here, we're going to have x squared all over x squared plus y squared, plus here we'll have y squared all over x squared plus y squared. Notice these two fractions have a common denominator, so we would have 1 plus the quantity x squared plus y squared all over x squared plus y squared. Notice how this fraction is equal to 1. So all of this simplifies to the square root of 2. So let's write this as the square root of 2 times the double integral over the region R of, now the integrand function is just x squared plus y squared minus the square root of the quantity x squared plus y squared differential A. Now from here, because the region R is bounded between two circles, let's write this using polar coordinates, where differential A is equal to r dr d theta and x squared plus y squared is equal to r squared. So in polar coordinates we would have the square root of 2 times the double integral over the region R of, again, x squared plus y squared is equal to r squared, minus, again, x squared plus y squared is equal to r squared, so we have minus square root of r squared, which would just be r, and differential A is equal to r dr d theta. And now we'll determine limits of integration for r and theta. Remember, the region R is this bounded region here between the two circles, and therefore the limits of integration for r are from 2 to 3, and limits of integration for theta would be from 0 to 2 pi all the way around the circle. Let's go and distribute the r. So we have the square root of 2 times the double integral, and we'd have r to the third minus r squared dr d theta. And now we integrate with respect to r. So the antiderivative is r to the fourth divided by 4 minus r to the third divided by 3. Now we need to find big F of b minus big F of a. So we have the square root of 2 times the integral from 0 to 2 pi. And then when r equals 3, we have 3 to the fourth divided by 4 minus 3 to the third divided by 3 minus, when r is 2, we have 2 to the fourth divided by 4 minus 2 to the third divided by 3. To save some time, I've already evaluated this. It comes out to 119 twelfths. So we have the square root of 2 times the integral from 0 to 2 pi of 119 twelfths d theta. Let's go ahead and factor out the 119 twelfths and continue on the next slide. So the antiderivative of 1 with respect to theta would just be theta. So we have 119 square root 2 divided by 12, and then theta. So evaluating here, we get 119 times the square root of 2 all over 12 times 2 pi minus 0. We have a common factor of 2. There's 1, 2, and 2, and 6 2s and 12. So the exact value of the surface integral is 119 square root 2 pi divided by 6. As a decimal, this is approximately 88.1172. I hope you found this helpful.